Hello everyone. Thank you for continuing to learn ultrasonic test technology with me. With the improvement of science and technology, many new technologies of ultrasonic testing have appeared in recent years, such as phase array, time of flight diffraction, and 3D focusing, etc., which are gradually being popularized and applied in the industry, especially the most widely application in ultrasonic phased array technology. The ultrasonic phased array refers to the use of software to individually control the pulse excitation time of each element in the phase array probe, thereby controlling the angle, focus position, and focus size of the emitted beam. In this sense, to a certain extent, this technology has the function of the ordinary straight probe, inclining probe and focused probe at the same time. First, let's look at the phased array probe. The phased array probe element is made of composite materials, and its signal-to-noise is 10 to 30 dB higher than that of conventional piezoelectric ceramic materials. During production, the composite material is first cut into several small wafers, usually 16 to 256 small wafers, and each wafer can be individually excited during use. These small wafers are arranged in a wafer array according to a certain rule, such as one-dimensional line, one-dimensional ring, two-dimensional rectangle, two-dimensional sector, etc. Combined with plastic wedges or delay blocks, these elements are equivalent to conventional oblique or delay probe. When paired with a straight plastic boot, this is equivalent to a regular straight probe. Direct contact and immersion probes can also be designed. Therefore, usually phased array probes are of the angular beam type. We know that conventional ultrasonic testing used a probe that both transmits and receives ultrasonic waves, or used a pair of probes, one for transmitting and one for receiving ultrasonic signals. The emission of the ultrasonic signal depends on the inclination angle of the wedge block to cause the delay of the sound wave at each point of the wafer, thereby changing the direction of entering the workpiece as the picture shows. While the ultrasonic signal reflected by the defect still relies on the angle wedge to produce a reception delay, only a certain phase of the beam will produce useful interference in the wafer, as shown in the figure. Phased array ultrasonic testing by changing the pulse excitation delay time of a single wafer or wafer group so as to control the ultrasonic sound beam to scan or deflect or focus according to a certain rule. As shown in figure, the soft excites 4 wafers at the same time at a time, and excites all wafers in sequence according to the set delay rule, so as to realize the ultrasonic scanning from left to right without moving the probe. This method is called electronic scanning. Adjust different delay rules to achieve ultrasonic beam deflection or focusing. Common forms of ultrasonic beam deflection or focusing are shown in the figure. When all the wafers are excited at the same time, a zero-angle ultrasonic signal is generated and the vertical incidence enters the workpiece, which is similar to the straight probe of ordinary ultrasonic testing. When a specific delay rule is adopted to cause arc excitation of the wafer, the focusing of the transmitted ultrasonic signal can be achieved, which is similar to the focusing probe effect of ordinary ultrasonic testing. When the wafer is excited with a forward delay or an inverse delay, the ultrasonic signal can be emitted at a certain angle, which is similar to the ultrasonic inspection of a common oblique probe. Due to the different spatial positions of the array elements to the probe wafer, the time for the reflected echo of the defect to reach each array element will also be different. The delayer calculates the receiving delay of each array element according to the receiving focal law, superimposes the echo signals to each array element in turn, and feeds it back to the signal receiving module. There are usually three methods for phased array ultrasonic inspection scanning, namely linear scanning, sector scanning, and deep focusing. A linear scan is an electric scan along the long side of the linear array probe to create a cross-sectional profile without moving the probe. In this scanning method, the ultrasonic signal can be of vertical incidence or angular incidence. A sector scan is a fixed aperture that electronically deflects the sound beam at different angle of the sequence transformation. In this scanning method, the probe does not move, but the transmitted ultrasonic signal can be continuously deflected within a certain angle range, which is equivalent to the detection of several ordinary oblique probes with different refraction angles. So, the detection's efficiency and detection sensitivity have been greatly improved. Depth focusing is a fixed aperture, and by controlling the excitation delay of each wafer in a group of wafers, the superposition of acoustic waves is achieved. This scanning method, in addition to realize the focusing of the sound beam, can also change the delay rules to obtain different focal lengths. When a defect is detected, the display of phased array technology is also different from conventional ultrasonic inspection, adding color image display. The basic process is: first, the receiving unit digitizes the amplitude of the received ultrasonic signal, and different numbers correspond to different colors. For example, red corresponds to the highest amplitude, and purple corresponds to the lowest amplitude. To sum up, the phased array technology realized electron beam deflection, focusing, and scanning by means of electronic scanning and different local lens laws. Therefore, it has the unique advantages in detecting workpieces with complex shapes. For example, stepped shafts, turbine blade roots, rotors, etc. Through discussion above, compared with traditional ultrasonic testing, we can see that phased array technology has the following technical advantages. 1. Real-time color imaging including A/B/C/D and S scan. Easy to interpret defects. 2. The phased array technology can realize the linear scanning, fan scanning, and dynamic depth focusing so that it has the characteristics of wide beam and multi-focus at the same time, so the detection speed can be faster. 3. The phased array has higher detection flexibility and it can realize functions that other conventional detection technologies cannot achieve, such as detection of complex workpieces. 4. It is easy to detect defects in various orientations and different positions with high defect detection rate, high quantitative and positioning accuracy. 5. The scanning devices is simple, easy to operate and maintain. 6. The test results are less affected by human factors and the data is easy to store, manage, and use. That's all for today. Thank you for watching.